Welcome to the Structural Intelligence Podcast, the show where we explore the intersection of engineering, technology, and innovation. I'm your host, Owen Keenan, structural engineer, entrepreneur, and tech enthusiast. Each episode brings together innovators, experts, and thought leaders who are pushing the boundaries of what's possible in engineering and technology. Through deep conversations and practical insights, we explore how new tools, techniques, and mindsets are reshaping our industry. We hope you enjoy this episode. Today, we have a guest that's somewhat special, who sits right at the intersection between these things. Brooke Smith is a chartered structural engineer and is the Head of Engineering R&D at ClearCalcs, a platform that many of us have used to perform our structural calculations. I certainly have. But Brooke's path hasn't been linear. From forensic engineering to open source development, he's worn a few hats, and that just reveals how broad his profession is becoming. In this episode, we'll walk through Brooke's career journey, the evolution of structural design tools from spreadsheets to cloud-based and AI systems, and how data is unlocking the new chapter in engineering efficiency. Brooks is joining us from Melbourne, and I'm over here in Perth. But Brooks, it's great to have you here, and welcome to the show.
Thanks very much, Owen. Thanks for having me.
Yeah, and I appreciate that, and it's good to talk across the divide. I guess that was my little bit of an introduction to yourself, but I'd love you to introduce you in your own words, and if you can give us a bit about your background, and maybe we can dive into a few things.
Yeah, so those of you good with accents would recognize that I'm actually from the New York City area originally. I grew up scattered throughout the Northeast U.S., including doing all of my university and graduate school training there. I've worked on a slew of projects in a whole lot of different fields, but I think I've never actually been a more traditional new design structural engineer. So we can talk about that journey that I went through, but overall, I like being on the weird edges where you can have perhaps a bit more creativity and I think a bit more excitement in what structural engineering is about.
That's great. Yeah, no worries. So I guess take us back to the beginning. How did your journey with engineering start?
So I always had an interest in mathematics, and I think always sort of on that STEM side of things, but I gradually drifted towards physics and then engineering as I discovered that I really wanted to have physical things in mind when I was working. I got tired of having everything represented by letters and wanted to have numbers instead in the work that I was doing. So throughout university, I just gradually drifted more and more towards engineering, and incorporating some of the other areas of interest that I've had into engineering as I went along as well.
Oh, that's great. Yeah. I actually started off myself. I did a Bachelor of Science doing physics and maths, and I think I gravitated towards the more practical because how can you apply these things? And that's so important. I know that I guess in that journey you had a different interests, like you mentioned. Some of them were maybe some more software side of things or open source. Can you sort of take us through some of those experiences just for a bit of context? And I guess this will set the scene for what we're looking to talk about in the future, but those sorts of applications that or experiences that you had with open source or software development.
Well, the somewhat amusing beginning I can give you to that was one of the early computers I had during middle school or high school was a Windows ME computer, and the darn thing got the blue screen of death every day. So yeah. I looked at what other options there were and installed Linux back in 1999 on my personal computer there. And Linux was pretty immature at the time, so you actually had to mess around with quite a lot of hardware settings and exactly how every bit of code was working in order to make your Wi-Fi transmitter work properly, in order to get the graphics card to get up to full resolution. And yeah, that brought me into open source initially and brought me to kind of my interest in computer science. I initially tried going through some computer science courses in high school, but actually found it to be too boring. Um, I know some of the developers who I work with right now will hate me saying that, but I actually find pure programming to be boring. And I wanted to find for my career something that I could merge it into to make it more interesting, and eventually gravitated towards structural engineering with that as well. But I've always kept an eye to the open source community, and knew like some of the tools that I started using in structural engineering. I'd find an occasional bug and go onto GitHub and submit a code update to go fix that bug. So I started with just little tiny changes like that, and gradually built up to now being the primary maintainer of a couple of different open source projects.
Yeah, great. What are those open source projects, just for our reference?
Yeah, so Anastruct and PyCUFSM. So Anastruct is a 2D finite element analysis package, which is meant to be extremely efficient and fast. So it's not able to do the really advanced ETAB style FEA, but is able to design a 2D truss in a fraction of a second. And PyCUFSM is very specialized towards cold form steel or aluminum or other thin-walled metals, and able to analyze the buckling behavior of those materials, again, rapidly and efficiently. It's actually a port of the MATLAB code for a program called CUFSM that was developed by one of my co-advisors when I was in grad school, by Ben Schaefer.
Yeah, great. Oh, that's great. So a few good applications there. So that's the software side of things. Do you want to just give us a little bit of a background of your nuts and bolts engineering journey, I suppose? And you mentioned you were a structural engineer, and what did that look like for you as you came through?
Yeah, so my first sort of career job out of school was working as a tester for Ansys. I tested the integration between Technically Fluent and Ansys Workbench. So that gave me some exposure early on to software and to quality control as well, and the vast importance of quality control. I believe I was actually the person who held up one of our releases in Ansys because I found a major bug. And for Ansys, it was extremely important because they develop software used in nuclear reactor design. So absolutely critical, highly regulated. I then moved to my first job out of grad school was as a forensic engineer. As I mentioned, I knew I really didn't want to go into just pure new construction design. And that was because I had the impression, I think a little overemphasized, but still generally true, that it was just plug and chug through the standards. And I did not want to plug and chug. I liked the idea of forensic engineering and finding what did the standard get wrong, or what did what wasn't considered in waterproofing that actually led to structural problems, or what didn't work in a building's design. Worked in that for a couple years, working on projects ranging from a bus terminal to the Empire State Building. That was a fun one, going through the Empire State Building with a hammer and knocking down chunks of concrete that just straight fell down almost on your foot. And gradually made my way into then a specialty consulting firm that did new product design in cold form steel. So I've always sort of had an interest also in that thin walled steel area, because there's really unique physics in there and exactly how the materials can buckle and how that affects the overall strength and behavior of the material. So worked in that for a few years before moving to Australia. And
that's great. Yeah,
finding
welcome to the
ClearCalcs.
Oz.
Indeed.
Yeah. No, that's that's a great journey, and I found a lot of value. I'm a lot into the forensic engineering realm myself. I do a lot of investigations type of work, and you really see how the materials and the nuts and bolts and the physics work, and when they don't work, and it gives you an appreciation of good design and not just the codified practice, which you mentioned. That's great. So thinking about, I guess your background leans really well to thinking about some of these concepts that we're going to be talking about here. So as we sort of move on, we have a lot of tools as engineers, all the way from sort of hand calcs to the calculators and then the list goes on to some more powerful software engineering packages or software analysis packages and things like that. And so I guess to set the scene, and from your experience with ClearCalcs as well, can you give us a feel for how you've seen engineering tools progress from, I suppose, 15 to 20 years ago till this point in time now, and how those transitions sort of worked, and maybe we can open up that conversation and ask a few more questions around that and unpack it a little bit.
Absolutely. So I think engineering has long been a field of finding tools that are viable, but not always necessarily the tool that is best suited or that was designed for structural engineering. So early on in my career, I saw most engineering work being done in either these giant FEA packages, things like ETAB, Strand 7, Riza, many others out there, or in Excel spreadsheets. You do the analysis in those big packages and then export everything into Microsoft Excel. Now, Microsoft Excel has a great purpose. I think it's absolutely fantastic for financial analysis, and that's what it's designed for. It's designed for accounting and finances. It's not great for engineering. For engineering, where you want to actually understand what equation is being used, it's really hard to parse and understand, is the math correct when it's doing A27 plus B75 divided by C76? Really hard to follow that math. So what started then developing were things like MathCAD, and some of the similar notepad style tools that actually showed you equations. Those still have some difficulty though, in that they're completely free reign. You can type anything into them, and while they have some limited unit awareness and unit control and some checking you can do with that, they're at the end of the day still reliant on a linear mathematics with few options inserted. So then I saw some of the local software starting to get developed more and more. Things like TEDS and Structural Toolkit, ClearCalcs in the US. But these are also all locally installed pieces of software. So they do some of the design, give you 10 input boxes, you type in numbers, and they spit out a result for you. What those did lose in that transition compared to a MathCAD, for example, is they don't show the equations being used. So that's long been a concern for a lot of structural licensed engineers. If you are going to take on the full liability of building design and sign off, yes, this is a safe building, you don't want a black box in there. You want to actually know the math that's going on. You don't necessarily have the time to go put together all of the math yourself, but you need to be able to be confident that yes, it is correct what is being done.
That's an interesting point. I think even the tools that we have developed over time, and I've used many over my career, is that it's always the factor of trust. And I suppose when we're thinking about the input in, if it's rubbish, the output is rubbish. That's the old adage that every engineer will use, and it is true to a lot of extent. But I think the transparency aspect of things, and no matter what tool it is, whether you're writing out a set of hand calculations that show your logic and workflow, or you've just done the calculations in your head, written the number down and written the result, that's a similar thing to putting it in a package and just trusting what comes out. But that's an interesting point on transparency. And so I guess to continue on from that, we've had some of these tools that I guess so locally done, and then where does it go from there? And what are you seeing now currently at the moment?
Seeing more and more go to becoming cloud platforms. So I obviously work for one of those companies, ClearCalcs, but there are a few others out there as well. And I see a lot of this becoming more widely available. I'll again Spruik open source a little bit. I'm seeing more and more software being available and incorporating open source software, even if it's not exclusively using open source. But incorporating all of these different tools that different experts in the field are bringing together into a coherent whole. So I guess the other thing I'd highlight with that is it doesn't dumb down the software because you still need to understand what's going on in it, but it does make it easier to use. So to create an accurate ETABS model, for example, you need to understand exactly the effect of different stiffnesses on connections and exactly the effect of putting a connection slightly offset versus exactly concentric or things like that. That understanding is vital to an accurate model, but we can also start to automate more of that. And even if we aren't automating it, at least flag, have you considered this? This is a little weird, this thing you're doing. Is that actually what you want? And I'm seeing more of that, more being brought in to help you along and make it easier for an engineer to do an accurate design without worrying about every tiny little nut and bolt, no pun intended, of the design itself.
Yeah, no, that's so true. The question that I had is sort of what problems are we solving better now than say 10 to 15 years before, and where do some like traditional methods excel?
Well, actually, I'll give you an example from next week. I'm going to be presenting at a cold form steel conference in the US about PySU FSM and some of how that software is changing the landscape of cold form steel design. Previously in cold form steel, you would typically be using span tables or very, very long form effective width calculations. Effectively changing the width that you're using in a calculation to compensate for the buckling behavior of that material. That's great. It can work. It is conservative, however. As we get further and further along in the tech like this, we can be more efficient. At the end of the day, engineering, unlike a lot of the public perception, is not about an answer being right or wrong. It's about optimizing. So we can now optimize that design more accurately. We can use the direct strength method in cold form steel, which gives a much more accurate capacity, but it's also much more involved to use. So being much more involved to use means that you need more tech to help drive it. And that can help us use more less material, so being more sustainable. It can help us reduce cost. It can help us just take away some of the inefficiency of engineering.
That's an interesting point. I think we talked about it before, where it's not just about right and wrong, is it? It's about different levers that you can pull as an engineer. And when you think about engineering judgment, I think it's really important to consider that you actually weigh up more than just the engineering or the numbers to other factors such as constructability, other factors such as material costs, scheduling, and a lot of different aspects that will come into play where the engineering judgment shines through, and the technician, the one aspect of it. And from what I hear you're saying is that there's certain things that we can optimize, but there's also certain things that we can take away from being, you don't have to do every single calculation or write out every single equation. You can take away that tedious nature of that, but you can understand and know it's correct as well.
Exactly.
Yeah.
And that doesn't mean that those hand calculations or Excel spreadsheets or some of those older tools don't still have their place. If you're designing the Burj Khalifa or a really unique suspension bridge or things that are more at the forefront, bleeding edge of structural engineering, then yeah, those are really useful tools, because there's not a standard calculation for designing the next Burj Khalifa. You have to do very customized calculations for that. And you still need those highly customizable tools for that. What the newer tools help with are the bulk of buildings, the ones that aren't as shiny, that don't make as much of the news, that the 90% of buildings that are houses and office buildings and yeah, the things you see on Google Maps when you scroll around.
That's right. It's our everyday built form where we take those things that are traditionally done. It might be taking away, making that more efficient, or making it more sustainable. Like you said, you can put a lot of different aspects into it. So that leads us to we've gone through and talked a little bit about where the tools have come from. A little bit about your background in cold form steel and also the development of things at ClearCalcs. And so as we move forward and having more of a forward thinking lens, we hear all these buzzwords such as AI, generative design, generative AI, and all of these things. And what I really wanted to do was to jump into that a little bit, but understand, okay, what are we actually talking about when we speak about AI as maybe a first thing, and then jump into that on how we can see that shaping what specific definition that we, I guess, decide today, or how we see that shaping our structural engineering practice moving forward, with a bit of the contrast of where the tools are now and where they've come from. And so I guess between yourself and myself, what would the definition of AI be for you in this context that we're talking about now? And I'm happy to offer some of my thoughts on that too.
Well, first I distinguish from, I think when most people hear AI, they think ChatGPT, Cloud, Gemini, the big LLMs out there, the large language models. And those are an important part of AI, and they actually have a place in structural engineering as well. But I think the area of AI that interests me most is not the LLMs. It's not the general purpose AIs that you type a question, they give you a final answer. It's the adaptive AIs and the AIs that have specific purposes. So I think about, for example, machine learning that makes use of historical data and builds it out into more optimizations that can be incorporated into design. And I think about limited scope AIs that can analyze different possibilities and their effect on a final design. Rearrange some restraints, use a slightly different member size, see what effects that has.
Yeah, no, that's so true. I think distinguishing, so from my perspective as well, it is distinguishing the different types And AI in and of itself can refer to a few different things, which is the large language models. That's a model of language. It understands a probabilistic model of how language works and what would be the next token or the next word, and it fills that in, and it can actually, with some reasoning, get pretty accurate results. And then when we think about machine learning, there's a set of data that we have, whether it might be structural engineering designs, it might be some other data around wind loading or wind codes or whatever it may be. And we can use that subset or the superset of data to extrapolate or to bring forward, whether it be an emergent design out of that, or something similar to that. So I think defining AI for this type of conversation and potentially for us as structural engineers is, I think it's the ability for us to be able to constructively use either a set of software systems or a process that can understand the raw and refined data that we have as engineers and be able to produce outputs that can assist us in our design workflows. And maybe that's a definition. Maybe it's not, but I think it's a good start anyway.
I'd agree with that. I think that takes us a good way through what we need.
So I guess having that as a background and a bit of a context, so let's talk about it for a bit. What role do you see it playing in today's structural design?
I see it, again, providing more means of optimization. And I see one of the biggest areas or I guess two big areas to use AI for are initial designs, getting something rough and generally accurate out the door, and for using data to further improve how we reach a design and ways of improving it. So I guess to elaborate a little bit more on that, we have a lot of data out there. We know all these buildings that have been built. With the advent of cloud platforms, a lot of data is available for exactly what numbers were used to complete a calculation. So what can we do with that now that we have all that data? We can run it through machine learning, and we can understand from that, well, if a manufacturer creates a new F6 stress grade for timber, to use a made-up example, maybe that's going to actually save us 5% of timber materials being used. We can analyze our standards that we've written. Standards are written to help ensure that we all design safely a building, but they also are not meant to be permanently static. We can go identify that clause in that standard is overly conservative. Nothing ever fails or comes close to failing based on that failure mode. Maybe we can loosen that up more. Or nobody makes use of this method defined in this standard. Let's go make it easier to use or refine it or make changes. And let's make use of that data.
It's interesting to think about where it's come, where we had a set of data which has informed our current standards or our current practices that we do as engineers. But now what we actually have is we actually have a sandbox where we can take more data and be able to play different scenarios on this and to see the emergent behaviors that come behind that. And I guess when I talk about emergent, it's properties that come from the system that you apply it to. So for example, we've got that set of data, we use machine learning on it, and what we'll find is that the data in and of itself is statically, it doesn't function. But when you put the learning on it and when you put the intelligence on it, what you'll start to see is you can you can effectively make some really close examples. Say you've got maybe a 3-story building and you want to size up the columns or the beams or the slabs. You can go, these are my dimensions overall. These are levels. This is the loading. Can you give us a first pass? And I think there's applications today that we can actually achieve that with what we've currently got. What would you say, and how would you describe that emergent design? And where do you think that's going?
Well, I'd add on that I think many consulting engineers should be excited by that idea of making a first pass with AI, because it means that you won't need to waste as much time on the bet of whether or not you might get that project you're quoting for. Run it through AI, train the AI based upon previous designs you've done, and you can come up with a pretty good, not something you can sign off on as a chartered or licensed engineer, but a pretty good initial guess for a design using AI. And you can save yourself a lot of time with that. But I see that emergent design enabling, again, just much more optimization throughout the industry and much more, it will introduce more problems. And I think that's actually an interesting area as well. This will not be a smooth road, and it's not going to be replacing jobs, but it's going to be introducing new abilities for engineers to work more efficiently. I would note, I think one of my favorite pieces of history in structural engineering is that until the 1980s, vibration design really wasn't a thing. We didn't design as efficiently. So those big bulky steel beams or concrete beams didn't really have issues with vibration. But as we started to be able to design buildings more efficiently using finite element analysis packages, and as a cultural change occurred where we started putting exercise rooms in office buildings, a whole lot of people moving in a rhythmic pattern creates vibration. And people who are sitting in a desk chair notice that vibration. So we had to then develop some new vibration codes to set standards for making sure those vibrations don't disturb users of a building. There will be more that will come out as we make buildings more efficient that's like that. There will, I am 100% certain, be more problems that we've just never thought of like that we'll need to consider in future standards and future design.
That's so true. I think where we're going is with technological advances are challenges that we're overcoming. We basically push the boundaries, and then sometimes it goes a little bit too far, and we realize what we learn, and we keep going forward in that iterative pattern. And what's really exciting to me about some of the technologies that I see coming through is it helps us to accelerate that iteration of that pattern. And what we'll be able to see is, you gave the example of the Burj Khalifa, what are the limits? That is a kilometer tall building. What are the limits? Can you go 2? Can you go 3? And but how can we do that most efficiently and most safely? And that's our responsibility as engineers. So, I guess in that topic of AI and particularly with your role at ClearCalcs, I'd love to, I guess, hear before we sort of finish up this conversation a little bit about what you do at ClearCalcs, and then what are some of the things that the current tools and things that you've got now, and sort of future forward looking in terms of what you guys are looking at the moment practically, because you are a cloud-based platform and things like that. So I'd be interested to hear.
Yeah, thanks for that one. Yeah, so my title right now at ClearCalcs is Head of Engineering R&D. It's a little bit of a vague title, but it's kind of I do a little of everything. I am a programmer working in our development team, and I'm also a licensed engineer in the US, chartered in Australia, and able to work across all of that. So my biggest role is how do we piece together all of these bits of tech with engineering that can be trusted? So we right now offer calculators, and a calculation builder is coming out in the next month or two, um, enabling anyone to build a calculator in a means that can be easily distributed and kept proprietary within your company. Many companies struggle right now with Excel spreadsheets. They spend a lot of time producing, walking out the door. Um, in a cloud platform, you can control that. And we are at the same time working on quite a bit in the AI realm. And I do want to allay concerns on that. When we're talking about AI, we're not talking about coming up with a final result. We're not talking about AI designing the entire building that you can just blindly sign off on. We are talking about how can you most easily come up with a first pass design that an engineer can then tweak, can then go use their creative skills to come up with considerations for sustainability, for constructability, for waterproofing, for getting getting plumbing pipelines through the building, for all the other concerns that you can then focus on. And we're making use of data to help manufacturers um, figure out what size beams they should be producing, and to help standards writers understand what clauses can or should be refined, and incorporating all of that into providing a cloud-based platform that can make you as an engineer able to be more efficient, creative, and safe.
Great. Yeah, that's great. So, who would be best to use all these tools that you've got? Give us a typical.
Um, well, right now ClearCalcs, at least, we are primarily tailored to engineers, but we do have a vision for enabling an architect to also be able to log in and create an initial design that they can then pass to an engineer. Um, but I think we're able to gradually incorporate just more and more of the design audience to be able to make use of these tools throughout the whole pathway. Right now, we used to have, actually, historically, we used to have one master builder who owned everything about a building design. Now we've split that up into smaller and smaller pieces with architects and engineers and quantity surveyors and lead contractors and subcontractors and all of these different bits and pieces. How can we unify them more into one place where all of them can talk together and iterate quickly?
That's great. Yeah, I love that notion of iterating quickly, but also the coordination of all of those different components and different experts and different disciplines, because that truly is what engineering is. So, in the spirit of the AI fashion, I'd love to hand it over to an AI host just to give us a little bit of a summary of what we talked about, but also to ask you maybe some concluding questions, and then we can go from there. Would that be okay? That's great. I'll hand you over now to the AI host.
Sometimes the hardest part of progress is letting go of the old ways that once defined us. In today's discussion with Brooks, we delved into how structural engineers are redefining their toolkit by embracing software, AI, and data. We saw how integrating these tools doesn't diminish our role, but elevates it, freeing us from tedious tasks and allowing us to engage in more creative and impactful design. Brooks, as we stand on the brink of this tech-driven era, what advice would you give to the next generation of engineers looking to find their place in this evolving landscape?
That's a great question. And I think I would urge everybody no matter what your interests are, if you're going into engineering, to understand the capabilities and limitations of all of the different tools out there. That will always, always, always be vital. You can ask ChatGPT a question, it can give you a great answer or it can give you garbage. And you need to understand what is going to lead to a good answer and how to use the tools available to you. There are a lot of specialties you can go into depending on your interests. I don't think everybody needs to be able to program, but programming is an important part of engineering as well. You can incorporate that and bring new tool development into our field, either via open source or commercial software. You can go into forensic engineering and understand all of the material behavior and exactly what can go right or wrong. But focus on some specialties you can bring in as well. Don't just assume engineering is going to be plug and chug, because that is going to be replaced. AI, machine learning, technology can get the routine done. Focus on something where you can be creative, where you can bring a new way of combining ways of thinking, new areas, new specialties into your field of engineering.
Absolutely. The fusion of specialties and the evolution of our roles can lead to unprecedented levels of innovation and efficiency. As AI takes on more routine tasks, engineers are free to push boundaries and innovate in ways we've only imagined. If this episode resonated with you, stay tuned for more insights on how we can harness technology to redefine what's possible in our field. We're just beginning to scratch the surface of what modern engineering can achieve.
Great. Thanks for that. I think it was a good little bit of a wrap up. And I've really enjoyed the conversation that we've had today. I think it's really relevant considering the things that are happening now, some of the technology that's coming through, but especially grateful for your background and understanding that intersection between tech and structural engineering, which is great. One thing is that I guess I know that the engineering toolkit is certainly not static, but all the tools have a certain purpose, and when we have the right tools at our disposal, we can do really, really great things. So I'd ask, do you have any final thoughts that you want to share with the audience, and what would they be?
I think we've had a great discussion today, and thank you very much for it, Owen. I think my biggest thought is just actually to re-emphasize, understand your tools, know the limitations and the capabilities. Everything is a tool. At the end of the day, you are the engineer who's going to be making final decisions and who can sign off on a safe design. No one tool is ever going to do that for you. So understand what the tools are in your toolbox and understand what they can and what they cannot do.
That's great. I think it's wise words. So if this episode made you rethink on how tech is shaping structural engineering, connect with us on LinkedIn. We love talking about things like the intersection of code, calcs, and the human side of engineering. So what we'll do is we'll actually drop some links to Brooks' projects, some of ClearCalcs' information there as well, and maybe some links to some of the open source contributions that he's made as well. So if you'd enjoyed the episode, consider subscribing, sharing with whoever might want it, some fellow engineers. And we've got some more episodes coming that explores the edges of our profession and how we can lead from them. Again, I just want to say a massive thank you. Thanks, Brooks, for being on the podcast, and look forward to catching up with you again soon.
Thank you, Owen.